Hello, everyone. Thank you for joining us today for this webinar titled UV Cured Powder Coating of Plasma Treated Heat-Sensitive Substrates. It is brought to you by Composites World and presented by Keyland Polymer. My name is Ginger Gardner and I'm a Senior Editor at Composites World. This webinar will discuss how the combination of a conductive primer, plasma treatment, and UV curable powder coatings is a viable way to finish heat-sensitive substrates without thermal damage or deformation. It will describe plasma treating, operating conditions, and surface condition measurements before and after plasma treating, as well as adhesion results on various substrates. Primary topics include application and performance benefits of plasma and UV powder coating, differences between types of coatings on heat-sensitive materials, and products and materials that benefit from this finishing technology. Our presenters today are Andrew Walton, Business Development at Keyland Polymer, and Project Manager Evan Knobloch. Andrew works with companies to develop new opportunities using UV powder coating in the military, aerospace, automotive, and healthcare industries. Prior to joining Keyland, he held a position as a specifications representative for DVUV, Keyland's sister company. He holds a BA from Fordham University. Evan Knobloch is a project manager at Keyland Polymer, working with customers to guide them through the project process, from receiving substrate samples to managing R&D trials, coordinating equipment suppliers, and technical support. Evan holds a BA in economics from Denison University. Thank you again for being with us, and now I'm going to hand it over to you, Andrew and Evan.
Well, thank you, Ginger, for the kind introduction. My name is Andrew Walton, as I've been introduced, and I've been with Keyland Polymer now for 13 lucky years, and we're excited to be speaking with you. So today we're going to go over some of the recent research and development that we've done, specifically talking about how we can bring the durability, speed, and efficiency of UV curable powder coatings to substrates that it was previously thought impossible to powder coat. So without further ado, I'm going to hand it off to my colleague Evan for an introduction.
Hi, my name is Evan Knobloch. Thank you for the introduction. I wish we could have met in person, but I'm grateful that Composites World was able to pivot and move this to an online platform where we could present this material that we find to be very useful. So without further ado, the agenda for today's presentation, I will provide a company overview, introduce industry opportunities by substrates, explain why they are difficult to finish. We'll introduce UV curable powder coatings and discuss adherence. After, I'll hand this presentation off to my colleague, Andy, and he will go over adhesion, introduce plasma treating technology, provide additional testing and results, and we'll follow with conclusions and questions from the audience. So the history of Keyland Polymer dates back to 2002 with a company called Decorative Veneer. It built the first UV cured powder coating system for MDF in North America. By 2005, we rebranded as DVUV and moved our operations from Michigan to its present state in Cleveland, Ohio. In 2006, we founded Keyland Polymer UV Powder to supply DVUV with UV curable powder coatings for their MDF line. In 2013, realizing that the majority of the performance properties in the coatings come from the resin and make up 60% of the material composition, we began Keyland UV resins to make solid resins in Spain to supply Keyland Polymer UV powder. And in 2019, we founded Keyland Polymer UV Materials Spain to produce and sell UV resins for the global market at scale for the coatings industry and additive manufacturing and for other opportunities. So if you look at our company overview, you can see that we are very much vertically integrated with R&D and manufacturing arms at all levels, from UV resin R&D and manufacturing to UV powder R&D and manufacturing. And then we have application know-how on heat-sensitive substrates with our DV-UV MDF powder coating line. And we can assist other companies with setting up systems utilizing the latest and greatest technology for application, melting, and curing of UV curable powder coatings. So what exactly are these industry opportunities? In front of you, I've laid out kind of examples from a couple different industries, specifically with the automotive industry. A blurb from the Department of Energy is reducing the weight of a vehicle by 10% yields a 6 to 8% increase in fuel economy. And from the Center for Automotive Research, by 2040, the estimated plastic and composite content in automobiles will increase to 15% from its current 6%. The two cars in front of you, the orange car on the left is the McLaren F1, which somehow looks futuristic, but was developed in 1990. It utilized a lot of Formula One technologies, and specifically carbon fiber. It was the first production vehicle to have a carbon fiber chassis, albeit at low production volumes and costing hundreds of thousands of dollars. Looking at the vehicle to your right, that is 23 years, the McLaren F1's Junior, being produced in 2013 for the first year, is the BMW i3. That car utilizes the same type of technology as the McLaren F1, but for an entirely different application, for a city car that favors long distances over going fast, and is environmentally sustainable and costing only $50,000. So you can kind of see the trend from high performance to more of every man's car eventually in this development. Furthermore, in the aerospace industry, you have the Boeing 777, which began flying at the same year as that McLaren F1 in 1990, with a material composition of 50% aluminum and only 12% composite materials. And the Boeing 787 Dreamliner, which began its operations in 2011, has a material composition of only 20% aluminum and 50% composite. And composite materials consist of 60,000 kilograms in one plane. So for additional areas, the medical device industry with wheelchairs and braces, and then sports equipment with your high-end bicycles, tennis rackets, and others. So these new materials are plastics, composites, and carbon fiber. They provide performance improvement in being lighter weight. It can be stronger and just overall better designed, opening up opportunities to design products in a much better way. They're more they can be more cost effective to produce as well, being injection molded or utilizing additive manufacturing technology, and can be rapidly prototyped to speed up the R&D process. Now, from a coatings perspective, these materials provide some difficulties to finish. We laid out 3 different problems here, which we will address and solve throughout this presentation. Problem 1 is that they are heat sensitive, meaning that they'll melt, deform, degrade, or outgas when exposed to excessive amounts of heat. Problem 2, they're not conductive, which leads to poor powder adherence or coating adherence onto the material. And then problem 3, they have a low surface energy and surface contaminants from how they're produced, which leads to poor to mediocre adhesion of the coating onto the substrate. So our solution to problem 1, problem 1 being substrates are heat sensitive, is UV curable powder coatings. Powder coatings have been around since the 1960s. They've been used primarily for metal applications. The image that you see in front of you, the top part is simulating a thermoset powder coating system. That is the traditional form of powder coating, where the material is applied in a powder form electrostatically onto the substrate, and then it is put into an oven where that coating will melt, flow, and cure over a period of 10 to 30 minutes and reaching temperatures up to 250 degrees C. Comparatively, UV curable powder coatings, the powder it looks exactly the same. However, it has photoinitiators within the coating itself that react to ultraviolet light. So the powder is applied electrostatically. It needs to melt and flow. So it needs to get to an elevated temperature of around 110 degrees C, which can be achieved in 1 to 4 minutes. After it's exposed to a high intensity ultraviolet light, we're utilizing UV LED technology now, which does not apply additional heat onto the substrate, where the coating then will be cross-linked and cured, and you have a finished product. So as you see, what I've kind of laid out is that it requires significantly less heat than traditional thermoset powder coatings. And the goal is to only melt the powder. So comparing this from a time and temperature standpoint, the yellow line is your UV curable powder coating system, and your green line is your thermoset system. The temperature of the coating only reaches 110 degrees C. At that point, it is sufficiently melted and flowed. Whereas for a thermoset system, it has to reach 120 degrees C, and it needs to sustain that for 20 whole minutes, which is the duration of the application, melt, and cure of a UV system. The total time for a thermoset system in this simulation is 60 minutes. So going back to that original goal of UV curable powder coatings, to only melt the powder and not the part, we have 3 images here of a polycarbonate plastic material that has been powder coated and then put into a gel oven, which is a medium range gas catalytic IR oven, for a total time of 120 seconds. At 96 seconds, that's when the part has been sufficiently flowed out. It only the surface of the coating only reaches 104 degrees C, which is enough for the coating to flow. We measured the temperature of the coating post-cure, and the surface of the material as well, which was only 85 degrees C. So the material itself was not deformed or warped in any way, shape, or form. So for additional advantages of UV curable powder coatings, comparing it to other coatings, liquid coatings, thermoset powder coatings, and then ultra low bake powder coatings, the benefits are that the systems can be significantly faster. They utilize up to 90% less energy. The systems are significantly smaller in a plant footprint. They're much more productive, which ultimately yields higher profits per hour. So moving on to the second problem, the substrate is not conductive. The solution here is conductive primers, but let's go back a little bit. The reason why, well, these materials are inherently not conductive, which means there will be low to no transfer efficiency of a coating onto the part. So the images that you see on your right here are plastic material. The top image is just the raw panel. The second image is an attempt to coat that material without the use of a conductive primer. And as you can see, there's little to no transfer efficiency of our powder coatings onto that part. However, conductive primers, which consist of an electrolyte solution in a liquid that is sprayed onto the part and then flashed off using heat or blown off with an air knife, will change the conductivity of the surface so the powder can adhere to it. And the bottom image is that same panel with a conductive primer applied and then flashed off right before coating and successfully coated with a white UV curable powder coating. So we've just discussed the problems and the solutions for problem number 1 and number 2. Now I will hand this presentation off to my colleague Andy, who will discuss the most interesting problem and solution, which is adhesion and plasma treating. So without further ado, here's Andrew.
Thank you, Evan. So yes, now we'll talk about the third problem, or the third part of this stool, that is coating heat-sensitive and non-conductive materials. It's low surface energy. As we know, many of these composites and materials have low surface energy and surface contaminants by their nature. One of the ways that we get around adjusting the surface energy and removing these contaminants is plasma treating. Similar to a metal finish where there might be a multi-stage wash, plasma does similar, has similar attributes. So it's going to remove some surface contamination, and it's also going to prepare the surface by changing it to be more receptive to a coating. So what is plasma? It's often referred to as the fourth state of matter. Lightning is an example of a partially ionized plasma that we're all familiar with. It's a partially ionized and neutralized gas mixture that contains physically active and chemically reactive species, so ions, electrons, and free radicals. Like a gas, it does not have a definite shape or volume, but unlike a gas, it's capable of being electrically conductive. It's formed by either high heat or electric energy. So for our testing and research and development, we used vacuum plasma technology. There's a few reasons we like it. In comparison to open air or atmospheric technology for plasma generation, which is most often used in inline production environments, vacuum plasma is extremely repeatable and consistent. So for our research and development purposes, that was obviously very important to us. Each part is treated equally and consistently, and it also eliminates the influence of atmospheric conditions. So the way that this vacuum plasma technology works is the sample is placed in the chamber, the air is evacuated, the desired input gas is put in, and that can be either argon, oxygen, ambient air, or others. And then you generate and apply an electromagnetic energy across the electrodes, which ionizes the gas in the chamber and forms plasma. And if you're looking for some more detail into this than we're going to go over in the presentation, Scott Subreme has a very good article in the February 2019 edition of UV EV technology. So that's a good resource. So this newly formed plasma affects the substrate by bombardment and also by forming oxy and amino functional groups on the surface. And these promote interface adhesion, and they remove organic contaminants, mold release agents, and those sorts of materials. So we can't see this optically, this change that occurs before and after plasma treating of a material, but it can be measured. Typically, it's measured with dyne testing. And what you see on the left is a high contact angle. So this is a pre-plasma treated part. And then on the right is the contact angle changing, so a after plasma treated part. So on the left, it's a high contact angle, has low wettability and low surface energy, which indicates it's a hydrophobic surface. On the right, it has a low contact angle, and this is after plasma, high wettability, high surface energy, which typically indicates a hydrophilic surface. And at the end of the day, it's good wettability that allows for maximum bonding strength between two materials. So to help visualize this, we put together a simple video. And what you're seeing here are two plastic substrates. One is untreated and the other is treated with plasma. And we're going to dip them into the water. And you'll see what this does. Immediately the water runs off. There's not much water staying on the substrate. However, after treating, we improve wettability drastically. And you'll see in just a moment here how the surface energy profile changes to improve wettability. And this increase can be temporary. It depends significantly on the material that's being used. But ideally, if we can increase the wettability, we can have good adhesion properties for the coating. So how do we test this? Excuse me. We use the standard ASTM 3359 method B, where a series of lattice cross marks are cut into the film down to the substrate. Many of you are probably familiar with this. Pressure sensitive tape is applied. It's then removed, and the amount of material removed is what is used with the graph on the right to judge the loss of adhesion. So ideally, we all want a 5B adhesion with no loss of material. The scale goes from a 0B to a 5B, with 0B being 65% or greater loss of material, all the way through, again, 5B, with zero loss of material. So what does this look like on some composites and plastic materials? Well, here we have four different substrates, three of which are plastic. So on material 1 is a polypropylene, material 2 is a TPO, 3 is a carbon composite, and 4 is a polycarbonate. And you can see these are all finished without any surface pretreatment, no plasma treating. We're getting very low levels of adhesion, 0Bs across to 3, and then a 1B on the polycarbonate on the material 4, which certainly would not be considered acceptable. After plasma treating, you can see very significant advances in adhesion. So we're at 5B for the first 3 materials again, and a 4B, which may be considered passable depending upon the application on the polycarbonate. So what I'd like to draw your attention to in this slide is the impact the process gases have on adhesion levels. So you can see the difference between gas 1, 2, and 3 on all of these materials. So it's not only the plasma treating process, but it's doing the little bit of research needed to determine which process gas is the ideal gas for that substrate. Another important thing to note is that if wattage is increased in the chamber, this can sometimes improve adhesion as well. And in this example on material 4, we see a doubling of adhesion. So here's a video which will show all of these steps we discussed. On how we would apply a UV curable powder coating to a heat-sensitive component. So again, first we're going to take that component, put it in the plasma chamber, evacuate the air, input the process gas, create the plasma, and 3D treat the surface. Now here's the conductive primer being applied and removed with compressed air. These materials can be either water, alcohol, or solvent-based. There's the electrostatic deposition of the powder onto the part. And then here we fondly name this Barney, and the part you'll see is going into its melt stage, approximately 1 minute. And after that, it's followed by UV, and in this example, it's UV LED for cure. Now the part, as you can see, can be handled quite easily. It's not hot. Now I'll do the standard ASTM 3359. We'll do a crosshatch. Use the pressure sensitive tape and judge adhesion against the chart. So these are some typical performance properties that we would expect to see on a UV curable powder coat, a typical gloss range, as well as our film build of 1.5 to 2 mils, ideally a 5B adhesion, pencil hardness somewhere between H and 4H, and we do not want to see any softening at 50 double rubs of MEK, and then obviously some good taper abrasion resistance as well. So we've done some third-party testing specifically for the aerospace industry. The results of this testing are the vertical burn. So these were conducted by AeroBlaze in Fort Worth, Texas. And this is the 12 and 60-second burn testing. So the substrate with the powder coat is exposed to a 1500 degree flame for 60 seconds. And then the amount of flame, drip of the flame, and burn length are all measured. And as you can see, we passed these flame tests. Same with toxicity. So this is the BOEING BSS 7239 test. So this one measures the gases that are emitted from the materials when they're exposed to flame. And both of the samples that we submitted were well under the parts per million threshold of the gases tested. So it's additional passing of that test. So these ideas are not new. Conductive primers, plasma pretreatment primers, they're not new technologies, but it's the combination of these technologies with UV curable powder coating that's exciting and new. It's this combination that brings the manufacturing efficiency and environmental benefits of powder coatings to substrates that it was previously thought impossible to powder coat. So we're excited to be talking about these new research that we've done. We feel it's opening up tremendous windows to bring again that efficiency of powder coatings to substrates that traditionally could not be powder coated. So to sum up, there's no solvents, there's no water. We use less energy and process parts with less time. So these can have some pretty strong impacts from a manufacturing perspective, reducing plant footprint, saving energy, lowering the cost of quality, and increasing the manufacturing flexibility and production capability. So these are simple ideas, but we're taking them very seriously.
So what you have learned here today is that plastics, composites, and carbon fiber are a viable alternative to traditional materials for the aerospace, automotive, consumer goods, and sports recreation industry. You've probably already known that. However, these materials are very difficult to finish, but as Andy mentioned on the previous slide, UV cured powder coatings in combination with conductive primer and plasma treating is an effective and efficient finishing system for coating these novel materials. So with that, thank you for taking the time to listen to both Andrew and I today, and we await your questions. Lastly, we used Nordson March, their equipment for plasma treatment technology, and we'd like to thank them and their efforts with working with us. So with that, we're here for the next half hour or so to answer any questions that you may have.
Thank you so much, Andy and Evan. That was great. We do have questions from our audience, so we will get started with those. In the meantime, those of you that are listening, please feel free to submit your questions by typing them into the question pane on your control panel at the right of your screen. We will get answers for all of the questions, even if we don't get to them while we're on the air. This webinar is being recorded and will be available online. So one of the first questions we have is, we need a coating system, pre-blend. I think it says that we pre-blend heavily with free radicals, scavengers, and HALs, which I don't know what those are. Will this be a problem for Keyland's product lines?
I can take that one. It's if I think I understand the question correctly, yes or no. I think what we, I don't want to sound so vague, but what we would certainly want to do is test. We have come across in the past a lot of applications where materials need to be, or materials are very sensitive to electrical pulse and we've done research to be able to determine that the application of a powder coat is not going to affect that component. There's also been certainly a lot of concern with some carbon fiber composite material that the exposure of intense UV energy could be detrimental to the resins in the matrix for those materials. And we've also done research that indicates, at least to us and to the customer that we were working with, that the amount of time that the part sees the UV energy is sort of so small that it's not going to overall affect it. So at the end of the day, it's something that we would certainly want to evaluate. But what we see is that our coatings, they're relatively thin, and they can accommodate a lot of different performance criteria and also blocking criteria. So that's certainly one we'd want to look further into.
In the application video, it appeared that the conductive primer was blown off with compressed gas immediately after application. Is that what I was seeing? Is that correct?
That is correct. As we mentioned earlier, in typical application settings, like for a full system, you would typically use some form of heat to flash it off, but other alternatives is using just an air knife to just spray the liquid off. So,
what is the solution composition of the conductive polymer? We've had that asked a couple different ways.
Sure. That's a good one. So we don't manufacture these conductive materials. There are a few companies that do, and they are capable of being made in water solutions as well as in alcohol and other solvents. They're a variety, and without sort of going, releasing trade secrets there, that we wouldn't, obviously we're not at liberty to, they're not our products, but the materials can be manufactured in a way so that they can be not only environmentally friendly, but very effective at setting a ground on the materials. And there are a handful of companies that manufacture the conductive primers out there. So I would encourage that person to reach out, and we can have a little bit more in-depth conversation about that.
One asked what powder chemistries other than TGIC are available?
So the powder chemistries that we were using for the comparison for the TGIC to UV, currently the backbone of UV curable powder coats are polyester. There's a lot of research and development that we're currently doing at our resin materials company, where we're looking at urethane, epoxy, and acrylic materials. Primarily, we're focusing on urethane polyesters. We have some epoxy materials as well, but most of our work up to this point has been with polyesters, and we're doing some pretty exciting research and development as well on the urethane materials.
Do you have any experience with BMC reflectors for automotive, UV treatment, and metallization?
Devin, go ahead. We both inhaled at the same time.
Yes.
At the moment, to my knowledge, we have not. I'm not necessarily completely familiar with the question. Andy, you might be a better person to answer this one.
Yes, if I'm understanding correctly, we've looked at putting clear coats over different materials. The problem that we've seen, at least from our perspective, is our coating's thickness. They tend to they're not as thin as some liquid applications, and in particular liquid UV applications that can be thinner films, which don't interfere with the reflectivity as much. So we have looked at it, and I think we were not an ideal candidate for that. It isn't to say that couldn't change in the future, but as of right now, I would think that that's probably not the best application for a UV curable powder coat.
For how long and at what power level is the plasma applied?
That varies depending upon the substrate. So some substrates, as I had alluded to, some substrates, the effective plasma will last only a few seconds, and for others, it'll last a few days or weeks. And it's balancing all of the factors, not only the energy, but the how much time the plasma sort of is in contact with the substrate, and then how soon after the coating is applied. It's balancing all of those variables together that we use to help determine what the ideal presets are for each particular substrate. And we've done quite a bit of R&D on a lot of different composites and plastics and printed materials. And although there are some good baselines that we've established, there really is no one recipe for each material. And that's kind of the beauty of composites. They can all be, and plastics, is that they can be designed in a way to increase performance in one area and then lower it in another area. And from what we've seen, I think to really directly answer the question, each substrate and each product is different, and it's really evaluating those materials to determine the best match for them.
So we've had several different questions about, is this powder coat process, can it be applied to a wide range of substrates composites? So what other plastics and what composites, and are there limiting factors in terms of application?
So yes, we've done a number of trials on different types of plastics and composites. It really, there's a lot of different types out there. That the way I like to explain it is, I mean, if somebody specs ABS, well, there's a lot of different companies that manufacture ABS, and it's not necessarily always the same formulation. So in ways, we prefer to do trialing in-house to make sure that we are able to achieve the performance required of a finish on that specific substrate. What we would need to know is, in a sense, the melt point or the deformation point of the material, and if it's a composite, what the resin is for in that composite material, and I guess what the performance requirements are for the coating and for what the application is.
So we've had questions, can you apply it on like polypropylene, polyamide? You've tested all those kinds of systems, right?
We've done polypropylene, we've done TPO, we've done polycarbonates, we've done various composites.
Okay. What is the relative cost of UV powder coatings compared to standard PCs?
So they used to be much more expensive, but the costs of a UV curable powder coat from a per pound perspective has been coming down quite significantly. And we'd like to think with the advent of our resin manufacturing business, we've been able to help that. I think one important note is that most standard powder coats will deform a composite or plastic substrate. So a lot of the low temperature powders that can be applied to these materials as well, we are going to be at the same price point or a little bit less expensive than a low temperature powder coat. So from if we were just to compare ourselves to a commodity bulk high temperature traditional powder coat that's applied to metal, we're going to be a little bit more expensive. However, if we're going to compare ourselves to a product that has similar attributes and similar capabilities, we're going to be at the same level.
And
what level of
sorry, I apologize. Ultimately too, you have to take into account the energy costs of the system itself, and what UV curable powder coatings offers, and just opening up the doors for finishing these types of materials that thermoset systems just are not going to be able to do. So,
what level of flame retardancy can you expect with a UV powder coating?
We've looked at adding flame retardant materials into the coatings themselves in the formulation, and they're a little bit difficult to work with, and that's true with a lot of additives. Because our melt window is relatively low compared to thermally cured powder coats and compared to low temperature powder coats, it's low and short, which is wonderful in a manufacturing perspective because it's less time, less money you're putting onto that part in terms of time and energy. it has a very limiting factor in the additives that we can use. So some of the more traditional materials don't tend to work as well in our UV curable systems. The burn testing that we have done, that's the latest information that we have in terms of how it does perform. And we'd be happy to share more details about that as well.
What is the storage stability of UV powder coatings?
Similar to a traditional thermal product, we do want to make sure we're not exposing it to direct sunlight. It'll clump in those instances. It's not going to cure, but it's similar to a standard thermally cured product. We do want to control the humidity and the temperature of the material, but it doesn't need to be kept like frigid. Just at ambient room temperature is fine.
Is your UV powder used for body panels, for example, like truck, bus, automotive, that are molded out of SMC, and can you attain like a Class A or a Class B rating?
Not yet. A Class A finish is just a little bit too smooth of a finish for a UV curable powder coating. You're not, unless you're putting a top coat over the top of that of the UV powder coating, you're not going to be able to achieve the smoothness you need for a Class A finish.
Can you use high intensity infrared for the melt flow gel, then UV for the cure?
Yes. The melt stage can be done with convection, whether it's shortwave IR or longwave IR, electric gas. The powder doesn't really care. Ideally, what we want to do is we want to try to melt it as quickly as possible and allow it to be so that it is prepared for cure. So the type of heat, the powder will perform well under any type of heat used for melt.
What is the resistivity of the powder coating? Do you offer any solutions for applications when lower surface resistivity of the coating is required for the application, for static dissipation, for example? Electric, obviously, resistivity.
Yeah, I know we've had one project in the past that was a concern. I know that. Go ahead, Evan.
No, go ahead, Andy. You're more knowledgeable on this.
I know that from our customer's perspective at the time, the coating did not interfere. It's a difficult question though to answer, because it is something that there are some variables that we can control in the coating, and they can greatly affect the outcome. I think it's. I apologize, but that's a difficult question to answer.
In short, I think we'd need to do a little bit more testing.
What is, and I don't know that you would know this because I'm not sure how many systems you've actually messed with, but what's the smallest footprint for the plasma treatment system that's safe to operate?
Good question.
How large was the system you worked with?
So we are using vacuum plasma. There is such a thing as atmospheric plasma that is more of a line of sight treatment, but can be put into a conveyorized system pretty easily. These can be built to sort of specification. So, I mean, the unit that we have in our facility is at a specific size where we can put in large larger dimension parts than what we normally work with, so that we don't, we're not limited. But if it's for a specific widget, I'm just looking at my cell phone for an example, they could most likely be designed in a way slightly larger than that specific widget, so you don't have to evacuate as much air, and so you would speed up your processing time.
Our products are a mix of plastic and metal components. Metal components are currently polyester powder coated, and the plastic components are wet painted, subcontracted. Can the UV powder paints be used on a paint line that is mixed metal and plastic?
So yes, it might not necessarily be the exact same powder formulation that's used on the metal component versus the plastic or the composite component, but yes, you can use the same system and tweak essentially the recipe of the powder, and in some cases, because parts are going to heat up and cool down at different rates, you may have to have oven settings adjusted for the part, but those recipes can be built and designed into the system so that, okay, in the morning we're going to run metal components, and in the afternoon we're going to run plastic, and it's just a matter of changing the recipe of the powder and the recipe of the system, or it could just be one of those factors as well.
But it wouldn't be possible to do both the metal and the plastic in one go, probably. Like, it would be hard to find a
It depends. There are some applications where we've used the same powder on a polycarbonate ABS blend and on an aluminum component, and they both worked well. The same powder had very good performance on both of those substrates. So it does vary depending upon the mix of materials. The tweaks in the powder might be small, they might be large, just depending upon the mix of material that we're working with.
What would the upper limit be in terms of final thickness of a UV powder polymer coating? We are interested in using a process for a semi-structural coating to a flexible and delicate substrate, and then to stiffen that substrate.
Good question. So for UV curable powder coatings, the standard film builds that we are trying to achieve for plastics and composites are typically 1.8 to 2.3 mils. There's no added benefit for applying thicker coating of our material onto the substrate. The reason is, well, what that means is that the savings is more put on or given to the person who's applying it. Then the material will go further, in a way.
And I think it's important to note that the thick films can be cured with UV. So we can properly cure a 3.5, 5 mil coating. However, sometimes that you can have adhesion issues. We can have loss of adhesion once the film gets high. And to Evan's point, you're essentially just putting more dollars on the part when you don't need to. So.
After plasma treatment, what is the value of the surface tension, for example, for a thermoset polyester resin? And he gave a 50 dyn per centimeter as an example.
Is he asking the surface tension of the coating or the surface tension of the material?
I think after the plasma treatment, what is the value of the surface tension on the material?
Oh, on the material.
Yeah, the material. Yeah.
70 dyne.
Yeah. Okay. This is interesting. Can your products be applied to composite wheels to increase the maximum operating temperature? You get the heat from the brakes. So, there is a lot of interest in like ceramic coatings and metallic coatings and that kind of thing that can increase temperature for composites.
So that's something that we're looking into. very high heat applications probably are not for us just yet, but I think some of the new research and development we're doing on these more robust resins, or different resins, I should say, may increase the performance. So that's an area that we're actively doing research and development on now.
And then I'm not sure I understand this question. It was, what about using double layer coating wet on dry? I'm not quite sure what.
If the question is about applying additional coats on top of UV powders, we have a lot of experience on that, specifically on MDF wood, where we're using the UV powder as a sort of almost a sealer, because it will, on a wood substrate that's porous, it's going to almost encapsulate that part, so that instead of having to put 5 coats of wet paint on it, you can just do a top coat and a seal or something like that. So we do have some experience with using a UV powder as a primer type of coat with additional liquid top coats on top of it. If that's the direction of the question, we haven't looked much at putting a UV powder on top of a liquid finish, and we have done it occasionally here and there, but it sometimes can wreak havoc with both intercoat adhesion on the between the layers of finish, and then the heating process needed to gel the powder or melt the powder, excuse me, sometimes can affect those coatings as well. So we tend to not coat on top of previously coated materials or recoat materials as well.
How does this technology compare to liquid UV coatings?
So with liquid UV, the materials are already in a suspension and they're ready to be cured. They typically, liquid UV materials can, well, let me take a step back, excuse me. Our materials are 100% solid, which has some real processing advantages to them. So that's why we need to do the melt step before the cure. With liquid, that's not the case, and there are some applications where liquid UV is a very good alternative. We do not do any liquid materials. We focus completely on solid UV powders and resins. Go ahead, Evan.
Well, I mean, in short, I mean, our materials don't smell. They're not. They don't irritate your skin, and just are much easier to handle in comparing them to liquid UV systems.
What types of applications or industries are you seeing the most interest from for this technology?
Well, actually, the ones that we laid out, the aerospace, automotive, and sports recreation equipment industries are the ones that are that we're seeing the most work in for UV curable powder coatings on both plastics and composites.
What is the particle size distribution of the powders?
I mean, it varies, but it's typically about the same particle size as a traditional thermoset powder coating, so 35 to 45 microns.
Do you need to use plasma and conductive primers on all substrates with this technology?
No, that is not the case. It's more for trialing and erroring. I mean, the way we operate our projects is we'll be provided the substrate and run a feasibility test on them without any additional steps. Based on those results, we will apply a conductive primer or utilize plasma treatment technology.
And just my own question, I'm curious, do you have durability testing you've done on these?
Yes. For what specifically?
Just curious how the durability would be on this type of coating. I imagine, I mean, I just have no clue if it would be how it compares to, you know, the state of the art that's out there now.
I mean, it's a lot of the questions are, or a lot of those answers are sort of on our website that you could
Okay.
check out. I mean, it really does kind of vary based on the type of material. But from a pencil, like the slide that actually that we could go back to is here, and you can kind of just look at just some of the standard testing that we've done.
So it's offering basically the same durability that you could get from other kinds of coating.
Exactly.
Yes, yeah, you would
perfect.
see very similar to a thermally cured powder coat.
Yep.
Okay, great. All right, well, we're getting up to the end of the hour. Thank you again to Andrew Walton and Evan Knobloch and Keyland Polymer for this webinar and for answering all of the questions today. If any of you want more information, please do reach out to these guys in the company, and it seems like they have more than capable ability to work with you and help you develop what you need. We appreciate everybody's participation, and we hope to see you again soon at the next Composites World webinar. Have a great day, everybody.